doing potential. And remember, potential is a scalar or vector quantity? Scalar quantity, very good. And that makes it a lot easier to work with than electric fields. Electric fields are kind of a pain in the butt to work with because you got to deal with the vectors and do all the vector analysis in addition to subtraction all the stuff. But scalar quantities are a lot easier because they're scalars, they don't have directions. So say, for example, this is a really simple problem. I just want to know the potential at point P at this point. And in order to find that potential, I'm just going to say V is equal to V1 plus V2 plus V3. So I just add them up, each individually, not worrying about directions or anything because it's scalar. And remember, our potential is KQ over R. So that's going to be KQ1 over R1 plus KQ2 over R2 plus KQ3 over R3. Now, because these are all the same, I can just say 3 times that quantity. So I'm just going to say 3 KQ over R. Because they're all identical charges, they're all 3 nanocoulombs, and they're all 1 meter. So it's going to be 3 times 9 times 10 to the 9th. Times Q, which is 3 nanocoulombs. 3 times 10 to the minus 9 coulombs. Divided by 1 meter. I remember this 3 came about just because there are 3 charges, right, that are all equidistant from the same point. So that gives me, what's that? These cancel. 81 volts. All right. Now, one thing that's a little bit different from what we've done before is that let's say that one of those charges was negative. So say, for example, Q3, instead of being 3 nanocoulombs, let's say it was negative 3 nanocoulombs. That means that the potential due to Q3 is going to be K is 9 times 10 to the 9th times negative 3 times 10 to the minus 9 divided by 1. That's 1 meter. So it's going to be negative 27 volts. So the difference here, we haven't done this with electric fields or electric forces where we carry those signs into the calculation, but we are going to do that for potential. So if you have a negative charge, that sign does carry over, okay? Is that clear? All right, so for example, if Q3 was negative instead, our total voltage would be V1 plus V2 plus V3, but remembering that V3 is a negative, and so that would be 27 plus 27 minus 27, which would be 27 volts. Because each charge contributes 27 volts, but one of them is negative, and so it comes away. Jose?
Would it be the same thing just to eliminate it from the beginning whenever you plot V1, V2, and V3?
What now?
Like, if all of them are the same, and the only difference is that one of them has a different sign, wouldn't you just be able to say V1 plus V2 minus V3?
Yeah, you can do that. It doesn't really matter where you put the sign,
Okay.
but I don't like to write it like that. But you can do it that way.
Just one.
All right.
So that's just Coulomb's law.
No, it's not Coulomb's law.
It's not squared.
It's
Because the R is not squared?
right. It's based on Coulomb's law. I mean, you can sort of do this. We didn't do the derivation for this, but you can sort of do it. You know, if we think force is work times displacement, and a voltage is roughly a work per charge, right? Or energy per charge. So we can say, let's see, that's going to be, or excuse me, work is force times displacement. Then we can say work then over charge is FD over charge. I'm just doing a dimensional thing here. So Coulomb's law gives KQQ over R squared divided by Q times D, and then one of my D's cancel, and then one of my Q's cancel. So I get KQ over R for voltage, or for potential. So it's related to Coulomb's law because we're working with that whole work thing, and Coulomb's law is sort of at its basic ideas derived from that. That's not a real derivation, that's just sort of dimensional analysis. Okay? So you certainly will have a problem. You'll see some in the homework where you have a collection of charges, and I ask you what is the potential due to those charges. All right. I'm going to add something else to it in just a second. Yeah. Let's try this one. There's a problem on the next page. We can try. I just have 3 charges, or 2 charges, and I want to know what is the potential at the top. So I want y'all to try that. I'm going to start if you like. You want me to go? Next page. Alright. Going. Alright, so this is that problem. Now here, I've written this kind of funny. I don't usually write them like this anymore, but Q is equal to 2 microcoulombs. That makes this charge plus 4 microcoulombs, 2 times 2, and this negative 8 microcoulombs. So I want to know what is the potential up here, right where its nose is. I just drew one. See, right there. What are you doing? I'm going to step out for a second. About 15, 20 more seconds. Try to wrap it up. Stop at 3:30. That's about 8 more seconds. Just guess if you don't know, or ask your neighbors. 3:30. Right, ask your neighbor. A is right. Very good. All right, so here, just like we did before, it's fairly straightforward, I think. Right, straightforward this? Yeah. You just say V is equal to V1 plus V2. That's going to be K times 4 microcoulombs times 10 to the minus 6. divided by R, which is 1 meter, plus K times negative 8 microcoulombs divided by 1 meter, and then that's equal to negative 36,000. Right, micro is 10 to the minus 6. And the K's are 9 times 10 to the 9th. So it's like that's 36 times 10 to the 3rd. I mean, yeah, 36,000 minus 72,000 is what this works out to be. Which is negative 36,000. Y'all think this tie goes with this shirt?
Random question
No.
alert. Random question alert.
My wife said the same thing. She said the pattern's not
I
right.
think
It has
okay,
blue in it,
similar.
and the shirt has.
it's similar, but it's a little contrasting.
You can only do most of the
I think
patterns
it
with the
goes
British.
with your personality.
What?
I think it goes with your personality.
Thank you. My daughter said that it would look a lot better with a hat, a top hat. She said a top hat. I should wear a top hat with it.
Yeah,
that's
but I
fish,
think
it's
you
fish.
should wear the top hat without
Right. Without the beard.
the hat.
And a top hat. Yeah.
You always have time to keep working on
Why don't we just throw in shoes?
I found that,
other things. Why don't we just throw in a cane?
Like, you know, I had that beard. Mary had a beard before, and now it's all women. Like when I first had the beard, like guys would say, "Hey, nice beard," and then women never said anything about the beard. But now that the beard's gone, all the women are like, "So nice beard." Old women especially, like old women are okay. I know that young women, they don't really say stuff like that, but old women, they say that because they can, I guess. All right. We since we missed a day, and y'all don't like derivations anyway, we're gonna bypass this. But let me just show you. It's kind of cool actually, because we've done stuff like this before. If we want to find the potential at a point P, like say here, but you're not going to be tested on this, because I just want to go through it quickly. We break our thing up into differential elements, and then I add up all those differential elements. And so to find the total potential, I just say the integral of the contribution of each differential element, which is the integral of k dq over r. All right, going from 0 to x equal L. And then you just define what in terms of what. We have to do a couple of things. Do you remember this? I mean, I don't remember, do you? Let me show you. You do k as lambda dx, where lambdas are, you don't need to write this down. I mean, you can if you want, but it's not going to be on the test. All right. And then you want to define r in terms of x, which is just d squared plus x squared. And then you just do that interval, which it's not terribly easy to do. Oh, you could probably do it if you're... I always use Shams. Do y'all know Shams' mathematical handbook? Yeah, you really need to get that if you're in Calc 2. It's like a whole bunch of integration tables, but it's a lot of other math stuff too. So you can pick this up in Shams, and it works out to be some natural log.
Cool.
Anyway, that's how you calculate the potential.
What is that after the K in the last one?
That's a D. Oh no, that's a lambda right here.
Yeah.
Lambda is a linear charge density. We did this last
Yeah,
semester, except we used it for not charge density, but a mass density. It's just a amount of charge per unit length.
No, I'm just trying to understand what it is.
And then when you do that interval, it comes out to be a natural log or something. All right, let's look now at potential energy. Can I go down from here? They seem really rapt over that for me to say that it's not going to be on the test. Y'all just want to know it to wow your friends.
That's why we write it.
Yeah.
Because we want to learn. That's why we're here.
Okay. Well, those types of things, you know, I really like. This is a very useful tool to be able to integrate over surfaces, and it comes up a lot in physics or engineering or whatever, chemistry, when you're integrating over a surface or over a collection of particles or something. It's a very useful skill to be able to have. and to be able to apply it in different situations. All right, so it said the potential at a point P is KQ over R. Right, so if I had this charge Q1 at a point P, I could find that potential. Now, I want to know how much energy is required in order to take a charge from over here and move it to right here. Okay? Because when I have this collection of particles, it's going to have a certain amount of energy wrapped up in it, and I want to be able to calculate how much energy that is. And that energy is going to be equal to the work required to take a charge from an infinite distance away and move it over to that point P. Can you all imagine that? I have a charge here. Yeah, Andrew?
Doesn't work increase only if you go up sideways?
What? In the gravitational field, yes. But we have this electric field here that's emitting in all directions, right? And now what, if I have a positive particle here, what is the direction of the force? Is it towards that charge or away from that charge? Yeah, it's away. That's a positive particle, so the force is in that direction. So I'm going to have to do positive or negative work in order to take it towards that charge. No. I'm going to have to do positive work because the force that I exert on the charge is in that direction.
So you were far gone.
Right, and so I bring this charge over here and I have to do positive work. Now if I let that charge go, they're going to fly apart, right? Because they have this energy contained within that configuration. And so we're going to figure out how much energy is in that configuration.
You just actually, I mean, an interesting way of thinking of it. It's the same thing with gravitational, except it's a different way. Because
Right.
it's just really big. Because if you move it left and right along a little line, a line around the thing,
The
it
energy.
will no work is done. But if you bring it closer to the center and farther away, work is done.
Right, we'll get to that actually. You're talking about equipotential lines. That's coming up next. All right, so if I remember that our voltage is just energy per charge, so if I want to find the potential energy, it's just going to be Q times V. So if I'm bringing a second charge, Q2, from an infinite distance away, and I want to find the change in potential energy for that charge, it's just going to be Q times V. And you want to be careful because this is going to be Q2 times V1. The charge of that second charge that I'm bringing in times the potential due to the first charge. And that's how my potential energy is being changed. And so I can get then an expression here, Q2 times K Q2 over Q1 over R. Or I can rewrite this as K Q1 Q2 over R. All right. Now, if I want to bring in multiple charges, and you'll have a problem next where you do this. Like, let's say I have 3 charges that I want to bring into play. We'll call this Q1, Q2, and Q3. I can find the potential energy held by this collection of charges. That's going to be K Q1, Q3 over R. I can find the potential energy due to this collection of charges, K Q1, Q2 over R, and the potential energy due to these set of charges, K Q what, Q what? Q2 and Q3 over R. And then the total potential energy, I'll call this PE1, 2, and 3, is just the sum of those 3. PE1 plus PE2 plus PE3. So I just add them all up. Now I do this a little bit differently in the homework problems. I don't know, I just recently sort of discovered that you could do it this way. And I think this is a lot easier by taking each combination of the charges and asking what is the potential. But you'll notice in the homework problems I'll do it slightly differently where I bring in each charge individually. Either way is correct, but I think this is a little easier. And we'll practice this way on the next problem. Right, so just like you did before with potential, you keep the sign of the charge. So if you have a negative charge, it's going to cause a negative potential energy. All right? Which means they're not going to fly apart, they're going to fly together. Okay? Now, if you have a larger collection of charges, and you won't see a larger collection of charges, But let's say that I had 4 charges instead, then you're just going to have a greater number of combinations. So you'll have like this combination, you'll have this combination, and you'll have this combination, right? And then you would have to do each combination for all the charges. You would have particle 2 and particle 3, particle 2 and particle 4, and what's the last one? Particle 3 and 1, and 3 and 4. And then you would have to add up all those different potential energies.
So 6
So did you
combinations.
do 1 and 3, so that you do 3 and 1?
Did I do 1 and 3? Oh yeah, no, you don't have to do 3 and 1, so you don't repeat them. Thank you, Ash. All right. But you won't see a 4. You won't see that. This is useful when you're talking about atoms and the makeup of molecules and what have you. It comes up that you'll need to determine the potential energy of collections of charges. That's sort of the biggest application of it. Not so much in circuits and what have you. Though this idea is behind circuits, that we have this potential energy when we're dealing with batteries and what have you. Okay, let's try a question. I'm going to skip this whole thing. I sort of do it differently now, just like in the past few days, and so that this whole thing is sort of moot. Let's try this quick test. Or, let's try the quick test. So let's just do this quick example. So if I want to find the work required to assemble these charges, it's just going to be K times 2 microcoulombs times -3 microcoulombs divided by the distance, which is 1 meter. So that 18 times 3 is 54 times 10 to the -3, right? So 0.054 joules. All right, let's try this quick test. Got 3 charges. Can I move down further?
Just a little bit.
If you're ready, go ahead and start on that quick test.
You can go down.
Remember, I do this funny thing. So this is 1 coulomb, 2 coulombs, and 4 coulombs. Those charges. Likely on Friday, if you see a question like this, it'll be a combination of potential and potential energy. Like I'll ask you, what is the potential at a certain point, and then what is potential energy in this collection of charges?
fun little tower defense game we should play. It's really cute.
They should just play board games.
I think they might like this. It's kind of a cool little puzzle game. It's kind of like a tower defense, but it's a puzzle. You try to protect zombies, but it's not fast. It's stomping zombies, and you plant plants to shoot them with peas and watch the zombies fall apart. Everyone's quite happy with killing zombies.
Right, right.
The government even agrees to that.
Here, folks, try to wrap it up. 20 or 30 more seconds. I'll stop at 3:30. I assume that's right. Just going to mark it right now. We'll come and see. So you all set A. So we want to take our three combinations. The potential energy of this combination is going to be 9 times 10 to the 9th times 1 times 2 over 2. This one's going to be 9 times 10 to the 9th times 1 times 4 over 2. And this one is 9 times 10 to the 9th 2 times 4 over 2. Pretty easy numbers to work with. We get 9 times 10 to the 9th plus 18 times 10 to the 9th plus 36 times 10 to the 9th. Is that 72 times 10 to the 9th? Is that right? No, 27 plus 36, so 63 times 10 to the 9th.
What's that? Which just said it's not there, so.
Well, no, it is 6.3 times 10 to the 10. That's the same.
No.
Right. The 72 is not there.
No, yeah, the 72, yeah.
Right. Okay. That's pretty simple, huh? All right. Let's go on to equipotential lines. Y'all did this in lab if you're in lab, but I know not everybody's in lab, but it's still a pretty simple concept. Equipotential lines is just a line where the potential is the same. That's why it's called an equipotential line, because it has the same potential, equal potentials. And along these lines, the change in potential is 0. Your potential doesn't change. So the work required to move a charge along an equipotential line, I'm going to abbreviate it as EP, is also 0. Remember, because voltage, our potential, is energy per charge. So if our potential doesn't change, our energy also is not going to change. And so along an equipotential line where the voltage remains constant, then the energy remains constant. Let's see, this was just delta V is VB minus VA, and that's our change in energy over our Q, if you want to fill that in. A rule about potential lines is that they're always perpendicular to the field line. So, for example, I would draw my equipotential line. What we usually draw as a dashed line, like that. And then you would have an infinite number of lines, as many as you want to draw, that extend outward like that. So I can have a couple points. Let's say I have a point here, point A, and point B. Which of those is the larger potential, point A or point B? Which is a larger potential? Click it in, either point A or point B. Which is the larger potential, A or B? Let's click it in. All right, I'll stop at 20.
Can you go up?
Sure. Yeah, B is the, is that good enough?
When I said that was unanimous.
Right. Go up.
Yeah, that's it. That's it.
Okay. So B is the larger potential, because remember V is KQ over R. And if R is small, B is big. Notice that if I have a point over here, then C is also the largest potential. So we'd say like this is a voltage equal to 2 volts. This is V equal 4 volts. And over here, this is also what, 2 or 4? This is also 4 volts. Now on a negative charge, it's opposite. So if I have equal potential lines, the further out I go, the larger potential. So this is the larger potential. Y'all understand why? Because it's negative, right? So it's getting smaller, but it's getting smaller negatively. So it's getting closer to 0. You understand? The magnitude is getting smaller, but it's getting closer to 0. So for example, like I would have negative 2 volts here and negative 4 volts here. So this equal potential line would have a larger voltage than the other, larger potential than the other. A smaller, excuse me. A larger. Larger. Closer to 0. All right? Now, let's look. In the lab, y'all worked with collections of charges. This is, what is this called when you have a plus and a minus? It's called a dipole. All right, so this is a dipole charge. One of your derivations is finding the electric field due to the dipole. But if we were, when we map out the electric field of a dipole, it looks like this. And if we map out the equal potential lines, I just draw them so that they're always perpendicular to the field lines. And they look something like this. And they're going to be symmetrical on either side. Notice that they're perpendicular to the field lines along each step as I go through. And do one right down the middle, it goes straight. And then it sort of looks like a basketball court. All right, so those are equal potential lines along that. And those surfaces or those lines, the potential is always the same. All right, so along equal potential lines, the potential is always the same, and the equal potential line is always perpendicular to the field line. That's really all you got to know. Let's try this quick test. I'm going to stop at 35. Excellent. E is right. These have the greatest value at points C and D. Right. Those are equal potential line. All right, we're going to do this last little topic. This is it looks complicated, but it's not terribly complicated, and it's fairly useful to know. If I know the I'm going to skip through the derivation since we're running short on time and just show you what it is that we're doing. So we'll just skip through this. And if I know the potential, so for example, here I have equal potential lines here, and then here, and here. And notice how they're spaced differently. So the greater the change in the potential, the charge will experience a greater amount of work, will experience a greater work. So when the potential changes a lot, the electric field is bigger. That should sort of make sense to you, right? Because if the potential changes a lot, that means that our energy is changing a lot, which means that we have big forces acting on it, than when the potential doesn't change a lot. Does that sort of intuitively make sense? That if the potential changes a lot, that means that you have a bigger electric field. When the potential changes a lot, that is the energy of the object changes a lot, your electric field is big. Whereas if it doesn't change that much, your electric field is small. All right, and so you can sort of read this like a topographical map. So here, the field lines are really close together, and on a topographical map, when the lines are really close together, that means you have a really steep hill, right? And here, they're further apart, and when they're further apart, that means that you have a flat piece of land, or flatter. All right, so it's a similar thing here. So I have a big change in potential up here, and a small change in potential there, over the same distance. All right, a steep hill and a shallow hill. All right, so when the potential changes a lot, the electric field is bigger. So we can have this relationship between the electric field and delta V. And remember, this change in something is kind of like a derivative. So this is a derivative, in sort of a very loose sense of the word. So we can define the electric field. I'm just going to give you the punchline. The electric field in a particular direction, I'll define what that means in just a second, is going to be the negative of the derivative of the voltage with respect to that direction. Right? The electric field is simply the derivative of the potential, the change in potential, by position. I go down to the next page. So for example, ES it's actually the negative dV ds. By the way, this is on your equation sheet, if I'm not mistaken. Can I see somebody's equation sheet? It's in the very back. No, it's not. Okay. Well. All right. So we can generalize this and say that in the x direction, it's the negative of the partial of v with respect to x. This symbol, which is the lowercase Greek letter del, means it's a partial derivative. And I'm going to show you what that means. It's really not that complicated at all. It's basically just like a regular derivative. EY is going to be negative del V del Y, and EZ, I'm going to write over here, is going to be the negative del V del Z. And then the total electric field is going to be EX in the I direction plus EY in the J direction plus EZ in the K direction. All right. I know it feels like we're sort of cramming this in at the end, and we are sort of, but students always do well in this part of the test, so it's a pretty simple question that I'm going to pose to you. So let's say that we have a potential. I have a potential that's given by some function. Let's just say it's x squared plus 3xy minus zx. All right, so I have some function, and I want to find the electric field. I've mapped out this voltage, this potential, in the lab, building a circuit or whatever, and I've created a voltage that looks like this in 3 dimensions. And that's the voltage given x, y, and z coordinates by that function. Now, if I want to know Ex, it's going to be the negative of the partial of V with respect to x. That's going to be the negative del del x of that function. x squared plus 3xy minus zx. Now, when you take a partial, you treat every other variable as a constant. So here I'm taking the partial with respect to x. So that means I'm going to treat my y and my z just as a constant value. I'm just going to treat it like a number, right? Because I'm not concerned with how it's changing. I'm only concerned with how x is changing. Because my derivative is with respect to x, not with respect to y or z. So I have multiple variables here, but I'm only considering x. So what is this first term going to be? It's going to be 2x. What is the next term going to be?
3y.
Plus 3y. What's the last term going to be? Minus z. See, so I have left in the, I've just treated each variable as a constant. Let's find ey. What is that going to equal? What's the first term? How does it change with respect to y? It's 0, right? So the derivative of that is 0. It's like the derivative of 2 with respect to y would be 0, right? What's the derivative of the next term?
3x.
Right, 3x. And the last term is 0. So my derivative here is just going to be negative 3x. Remember that negative comes from right here, from the definition. And then easy negative del v is just going to be negative of negative x, right, which is equal to positive x. Then, because there is no z here, there is no z here, I only have a z here. See how easy that is? That's simple. Partial derivatives?
It's just derivatives.
Right, they're just derivatives.
Normal derivatives.
They're not really normal derivatives because you have multiple variables.
Yeah, but it's
But
we're taking partial, so it's acting like a normal.
right, we're only looking at how the function changes with respect to one variable. And in that way you can map it out in 3 dimensions. All right. Now, let's say that we want to know what is the electric field at coordinates 0, 0, 1. At x equals 0, y equals 0, and z equal 1. That's going to be ex in the I direction, plus ey in the j direction, plus ez in the k direction. Y'all familiar when I say IJK? Chow, Lin Ping, Mary? No. Okay, those are unit vectors. The I vector denotes in the x direction, the j vector denotes in the y direction, and the k vector denotes in the z direction. Those are unit vectors. They have a quantity equal to 1, but they just show the direction. It just shows that this is the x component, the y component, and the z component of the vector. We can go over it later if y'all want. If you don't remember, if you didn't do that. So here I would just take my coordinates and plug them into the individual functions. So up here I would put in 0, 0, 1. So that would be this term would go away, that term would go away, and I would be left with negative of negative 1, which is 1i. And then I would do the same here. What was that? X was 0, so that's going to be plus 0j. And then EZ is also 0k. Because I'll take this function and plug in x equals 0. All right? All right. Listen, there's a problem here. I'm going to leave this on your own to do it because I want to go through a few of the concept test questions. So we haven't gotten to do many of those. Y'all okay with this? Yeah?
He gave us a problem. This one, would we have to draw it as well?
Draw it? Oh, no.
Okay.
No. That would be very difficult to draw. The potential, you mean? Or the electric?
The direction, once we have points, what, whatever.
No, I would just ask for the electric field, and then it would be, if I give you this question, it's going to look just like this. So it's sort of a gimme, right? Not for a 3D vector, no. I mean, you will have to do that for electric forces or electric fields. You will have a 2D vector problem. But, what was that?
Three dimensions just get too
Uh-huh.
hard. Can't draw three dimensions.
Easily.
Just make it easy, like
It was something. Yeah. I said easy.
Yeah.
So they started having numbers larger than 2. Pretty sure easy is.
So what was your final answer, Pete?
Final answer was just 1 in the I direction. Yeah, so the final answer is 1I. And that's in newtons per coulomb or volts per meter. That's a really nice way to find the electric field. If you know the potential function, you just take the derivative of it. It's a lot easier to find the electric field in that way. Alrighty?
What was the unit?
Newtons per coulomb. Alright folks, I want to highlight a few. We don't have time to go through all the concept tests. I know this was sort of rushed at the end. I'm sorry for that, but it's good. That should be an easy 10 points on the test, right? What? No, you're supposed to say yes.
I'm lost.
Okay, well I can help you with it if you like. Or the homework. Once you get the hang of it, it's
You good to go.
good to go. Yeah, it's just a derivative really. It's nothing fancy.
Can you give us the answers to the?
Ooh, I don't know the answer. I can do it real quick. So EX is going to be, oh yeah, yeah. I'm gonna post this actually online. I just wanted to point out a few things. Here, we have an electron and a proton and an electric field. They both feel the same force but opposite directions. Remember, F is equal to QE here. So even though the proton and electron are different sizes, they feel the same force because it's F equals QE. Here, the electron has a greater acceleration because it's smaller. Same force, smaller mass, bigger acceleration. Now here, this one tricks people. Now the electron's going faster here, right? So you'd think that it would have more kinetic energy, but the mass is so much smaller that they actually have the same amount of kinetic energy. And you can think about that in terms of this, that my change in energy is equal to Q times V. Now they both experience the same change in potential, and they both have the same charge, so they have the same energy. This is combining those charges like we did. If you were to combine these three charges, finding the potential energy, you would do K, Q, Q over R for these two. And then you would have similar K, Q, Q over R for these two, and K, Q, Q over R for these two sets of charges. But if you combine these charges, it's just K, 2Q, Q over R. So this assembly requires more work. All right. Let's get this. We had a question like this. Actually, let me go to the next one. Go to this one. We had a question similar to this. Here I want to find where the potential is equal to 0 at the points on the x-axis. Notice, like for example, with this configuration of charges, this charge is not the same distance from the axis as that charge, so that potential is not equal to 0 because they don't cancel out. Whereas over here on this configuration, these two charges are the same distance, and so they do cancel out. The potentials of those charges do cancel out. Why do they cancel out? Same distance, but also opposite signs, right. So I have a plus and a minus, so they cancel out. Remember, they're scalar quantities, so they just add up like numbers.
Did you have it drawn in?
Huh?
Did you have it drawn in the lines?
The x-axis, you mean?
Like the vectors or whatever in the dot?
You don't have to draw any vectors because you're looking at potentials. Can you repeat your question? I'm not sure if I
Like the
understand.
dots and stuff, if you have the dot placed on the graph and the line drawn?
No, like none of this would be.
And they all look exactly the same.
They're not though. See how the charges are arranged differently?
Oh.
Like here, this is a +2, +1, -2, -1. Well, look here, they're switched like that. So it depends. You have to look at each individual configuration. So like, for example, over here, if I pick a point, these two charges are different distances, so their potentials don't cancel out.
So it's only A and B point.
So A is the right answer, right? Andrew?
Why do you put your point charge right there on the x-axis? Why do you think that's?
That's because that's what the question asks. Where does V equal 0 at all points on the x-axis? Yeah, I know this is fast.
It's like the point is traveling through.
Right.
Where would it equal 0? On the A, on one of them it'll start shoving it around. On A, at all points across that line it'll equal.
Right. It's a similar one. Here I want to know about work. We sort of talked about this. I want to know which requires the most work for a positive particle. The most work is going to be in this direction, because I have to apply a force in that direction, and so I get a positive work. 0 work would be what direction? 3 would be 0 work. Negative work would be what, Chow? 4. Yeah, negative work would be 4. Because then the field is pushing my charge that way, so I don't have to do anything. Actually, I'm just trying to slow it down, actually. I'm doing negative work on it. Okay, I think that's the gist of it. Oh, yes, yes. I'm sorry, guys. Listen, I have a screencast up for the concept test. So, I mean, I'll put the solutions up, but you can also find the screencast too. And problems are going to be 1 through 6.
1 through 6?
Right. No capacitors. Like if you're looking back at old tests, if you look at the old tests, I have that question distribution, but it doesn't split up chapter 2. But basically, if you see a capacitor, that's not going to be on the test. Right. The format for the test will be similar to before. 15 is multiple choice, 4 to 6 free response. Guys, listen. If you haven't had me before, on the free response, you need to, if you write nothing, I'll count all the points. But if you write something that's even close to right, you'll get something. So it behooves you to write something on this question. As close as you can get. Is that clear? Right. And that's 70 points.
Do you get partial credit for like right out like doing the other problems?
Huh?
Do you get
For multiple choice?
Yeah. No, not multiple choice. Like I'm talking about. Yeah, like equations.
If you write something.
You got like run the equation, everything. Like you get your small math afterwards.
Oh yeah, I count on maybe a point or two. All right. Y'all have a good day. Listen, if you have questions about the exam, the new folks, my question. A good feel for the exam is to look at the back. I have some old exams you can take a look at, and that's going to be the format that you'll have. There'll be multiple choice questions followed by free response questions. All right, the multiple choice are 30, the free response are 70. Okay. Bye, Jose. Is that clear, y'all? Linping, is this fine? Yeah. Okay. I would practice those old exams. They're good practice for y'all.